just to start with, I'll just give you a little bit of background to VegWatch, or the Vegetable Industry Biosecurity and Business Continuity Strategy. It's a 5-year project that's funded by Hort Innovation using the Vegetable Fund research and development levies and contributions from the Australian government. It's a partnership between AUSVEG, Plant Health Australia, the Department of Environment and Climate Change Victoria, Queensland Department of Primary Industries, the Centre of Excellence for Biosecurity Risk Analysis at the University of Melbourne, OnSide, and the RM Consulting Group. And just a little bit of background about the vegetable industry and why we actually care about pests. So AUSVEG represents more than 3,600 growers around the country that produce more than 3.6 million tonnes of vegetables worth $5.6 billion. So it's not a small industry. We represent a lot of different crops. And one of the important things to note is that most of that produce is traded domestically, which can sometimes present some challenges when a new pest arrives. And over the last years, we've seen a number of these challenges arise, and the impacts on growers can be quite large. And you can see some of the examples here. So recently we've been involved in, and this is just a small number, not the ones in the last 6 to 12 months, but we've had guava root knot nematode, tomato potato psyllid, fall armyworm, tomato brown rugose, fruit virus, more recently the potato mop top virus in Tasmania. And history shows that when the vegetable industry has been better prepared, we've been able to respond more effectively as well. The VegWatch program was constructed really to make sure that the industry is better prepared when a new pest arrives, and that growers can adjust and resume trade more quickly and as smoothly as possible. So the intended outcomes from this program are to develop and deliver a robust and responsive biosecurity framework for the Australian vegetable industry that includes the ability to detect our key pests earlier, to respond more rapidly and effectively when a pest comes into the country, and to support business resilience and continuity so that we can keep growers in business and also strengthen the trust between the industry and AUSVEG and the greater biosecurity continuum. So this is the team that is doing it. Or most of the team that's doing it. Some people were missing on the day. So the program is comprised of 3 themes. These are business continuity and trade, which is led by Plant Health Australia with support from AUSVEG, surveillance and diagnostics, which is being led by DECA, or Agriculture Victoria, SEBRA, and QDPI, and data and decision making, which is now involves AUSVEG, and we've also been working with OnSide in this component, and the whole program is managed by AUSVEG. And the goal really is that we have tools on the shelf and systems ready for when a new pest comes into the country, that we can rapidly support recovery, decision-making, and return to trade. So essentially, this is how it all joins together. We have started with the development or revision of a biosecurity plan, and which was led by Plant Health Australia. Steve Correll will talk about that shortly. From this, we've identified our key priority pests in which we will invest in risk maps, surveillance options, and diagnostic protocols so that we can inform surveillance methods and accurately identify the pests when we find them or they're reported. And then ultimately, the goal also is to collect data into a central portal. So industry will be conducting surveillance to collect not just when we find a pest, but also zeros. So it's really important that we have zeros and we know when a pest is absent, so that we can demonstrate that, freedom of in an area or a site from that particular pest to support return to trade. We've also been working with OnSide, which Guy will talk about a little bit later, to evaluate how we can use farm visitor and farm movement data to support traceability in a response. So, and then we've also the Farm Biosecurity program within AUSVEG that's supported by Plant Health Australia is also developing or has developed a new Farm Biosecurity manual to support growers to implement good practices on their farms as well. So to get on to what we're talking about today, so this is the outline of what we'll present to you. So Steve Quarrell from Plant Health Australia will share what Plant Health Australia has been working on with the Industry Biosecurity Plan. Paul Campbell from QDPI will talk about the diagnostic capabilities and why they're important. So making sure that we've got the right pest, or it is what we think it is. Tim Hurst, who's leading the surveillance component, will talk about the surveillance protocols that we're developing. James Kamat from the Centre of Excellence for Biosecurity Risk Analysis at the University of Melbourne will tell you a bit about the risk modelling that we've been doing and how that can be used or is being used. And then we'll finish with Guy Davison from Onsite to tell you a bit about the project and how that contributed to visitor movement data, and finish up with any discussions. There'll be an opportunity to ask questions at the end of every presentation too. So I will now once I can stop sharing. I will now hand over to Stephen Quarrell. So Stephen Quarrell is the Manager of Biosecurity and Planning with Plant Health Australia and an experienced entomologist. We've had lots of good chats about bugs. So I will hand over to Steve. Thank you.
Cool. Thanks, Rose. Hey, everybody. Welcome. I suppose the first thing we need to know if we're trying to work out what the biosecurity issues are or improve biosecurity for the vegetable industry is to actually understand what the threats are. So as Rose said, what are the risks to the industry? So to do that, one of the first things that we've done as a part of the project is to develop a biosecurity plan that helps us to identify the exotic pests and diseases that could impact on vegetable production and trade, determine which of those species pose the greatest risk to the vegetable industry, determine I'll do a stock take of resources that are available for those pests so we can try and identify where the gaps are and where future investment needs to be directed. And then finally, as you can imagine, once we understand what those threats are, what the gaps are, is trying to work out what we can do to strategically invest in the industry to improve their biosecurity preparedness against those exotic pests and diseases. So one of those things that we do is, to get that to work, is to work out what the high priority pests are for the industry. So for some of you in the audience, you've probably been involved in technical review panels, but basically we go through and we do a bit of a stock take of all these pests and diseases that are external to Australia that might impact on, in this case, vegetable production and trade. Hold a technical review panel, so work with industry and government to review these species and develop risk ratings. And then on that basis, work out what the high priority pests are for the industry. And that's really based on their entry potential, so their ability or the pathways into Australia that enable them to get into the country in the first place. Determine whether they're able to establish in Australia, so are there the biotic and abiotic factors that are available here in Australia, so the food resources, the climate and whatnot that enable them to establish. Look at their spread potential. So, what are the movement, how would they move within the country? If you've got a thing like a fall armyworm that was a really strong flyer, was able to move around the country quite freely and, assisted by wind currents. But there's other things, viruses, bacteria and all those types of things, nematodes that have different pathways around the country or movement potential based on, the movement of unclean machinery, boots, people, all those types of things, or the movement of plant material. So there's spread potential. And then finally, and most importantly, for the vegetable industry to work out what the potential economic impact is of those pests if they do get in. Not all pests are created equal, fortunately. Some aren't going to have a huge economic impact. They're going to be managed by current management practices pretty well. Some of them are just another aphid, but others clearly aren't, so, and they're the pests that we really need to start worrying about. So once we've got the high priority pests developed, when we did this review, we ended up with about 28 species that we need to be concerned about. So there's 10 pathogens, and some of them you'd know about, so CLSO, A lot of people would know about CLSO, that it impacts potatoes, but it also can have a severe impact on the carrot industry as well. Windborne funguses like onion leaf blight, but a lot of viruses as well, so chili leaf curl, all those types of things. Potato tumor nematode doesn't just eat potatoes, unfortunately. Also impacts on a lot of other crops, and then about another 17 invertebrates. So brown marmorated stink bug that you'd all know about, giant African land snails, striped cucurbit beetles, all sorts of things. So carrot rust fly. So a lot of things out there that could potentially impact on the industry if they get in the country. So then, of course, I said, we'll do a stock take, and then we sort of develop an action plan. So, right, what are we going to do about this, given that we know what these threats are to the industry? So how can the industry prepare, detect, and respond to these exotic pest threats? So one of the things is we develop an action plan. And again, we worked heavily with industry and with government to try and work out what can be done about these pests and diseases. How can we detect them, how we can better prepare for them, like Rose said before about TPP. How can we detect them through good surveillance and diagnostics? And you'll hear more about that later in the showcase. Or, how as an industry can you respond? What management practices are available internationally that it can enable that to happen effectively? So we've gone through and developed an action plan that has, and I should have counted, a number of different activities, that are both on-farm activities that growers can do to try and improve their preparedness, but also resources that sit within, say, AUSVEG that can be utilised if an incursion occurs. So things like a Biosecurity standard operating procedure, so a BISOP, calculating or maintaining the ORC framework. So if things get in, how can vegetable growers be reimbursed? But also, as I said, on-farm resources, biosecurity, planning manuals, fact sheets, all these types of things that'll help support the industry moving forward. And I think that's me, Rose. So I suppose the next step for us is really also to have a look at, we're going to sort of move into this other space about trying to work out what management strategies are available through industry as well. So if some of these things get in, yeah.
Cool, thanks, Steve. Here I was thinking I'd have to keep you all to time, and you're just doing great. So no one's put any questions in the Q&A, but if you do have any questions, that we're using the Q&A function if you want to type in any. I'll just make a statement around this. So one of the things that we've come up against is that we have 28 species in our priority pest list, which is a lot of, well, yes, AUSVEG represents a lot of crops, but it's a lot of species that we potentially could go to a response with. So our next step in this space is to work out which of these pests we would consider to be able to be eradicated, or which ones we would be more likely to go to management for. And so that's kind of where we're at in that space. And for those pests that we, work out what we need in that space, if we do decide that these ones are worth eradicating because the impact is really quite severe, then what do we need to have in place for those pests moving forward? Or if we go to management, have we got enough tools already for growers to manage those pests if they do come in, or do they even fit into existing management practices on farms? So that's where we're sort of heading to in that space at the moment. Oh gosh, Steve, you do have a question. So when prioritising pests, many established methods do not require future planning through long-term or short-term impacts. Was this considered in the HPP stage of the VegWatch?
So did we consider climate change within the high priority pests? Yeah, so no, because I think to do that, we'd have to go through and do climate modelling and that to try and work out what that'd be. And that is sort of the sort of activity that you'd put within the action plan rather than doing it during the actual biosecurity planning phase. I think that's the quick answer to that one.
Great. All right, and hopefully, Stephanie, I answered the second part of the short term with the, we'll now use that priority pest list to determine what kind of tools we need to have in place if those pests are detected. Alrighty, if there's no other questions, we'll move on. So our next presenter is Tim Hurst. So Tim is the Senior Officer Plant Surveillance with Agriculture Victoria, and he leads the surveillance component of this program.
Thanks, Rose. Let me poorly share my screen. Okay, can everyone see that? Thumbs up, very good. Great, all right. I'll be talking today about how technical reference guides guide surveillance. For those of you who've been over the journey for quite some time, technical reference guides are what we used to call national surveillance protocols. We've had a name change and a structure change to make them more fit for purpose. And so I can run through some of that today. So I poached that from Aaron Dodd. He's in the chat, so I'll just move on from there because I don't want to have to bungle it. Surveillance, it's simple, right? So most of the people in this chat and the project will know that everyone thinks they're a surveillance expert because surveillance is just having a look for things, and it's not quite that simple, and that's why we need a technical reference guide. So at a minimum, there's kind of two different types of surveillance when we think about surveillance. There's specific, which is pest-specific risk-based targeted surveillance. It's risk-specific, and that's what Stephen was just talking about. It's location-specific. We talk about modelling, entry and establishment pathways. That's what James will talk about later on. Then you start to get into the kind of biology of the pest. It's time-specific, how you catch it, it's method-specific, and it's goal-specific. So there's a lot to consider when we're kind of mapping out a surveillance plan for what we call specific surveillance. Then we have general surveillance, which kind of encapsulates everything else. It's a very confusing term. It's a bit of a catch-all, but it starts to catch things like public reporting, biosecurity blitzes, collection and collation of industry data, as well as creating and maintaining systems to kind of capture, collate and report on all of this data. You're getting a surveillance 101. For surveillance, context is very important as well. It really depends on what you're trying to do, and these are generally kind of agreed to terms in the surveillance world, and these are your different goals. We've got early detection, so that's about detecting incursions of plant pests before they spread and become widely established to allow for implementing appropriate management strategies. Delimiting generally occurs when something has popped up, and we need to have an idea of where it is and where it isn't, which will inform containment and eradication. So surveillance related to containment and eradication is generally providing that evidence-based information to demonstrate that control measures put in place are working and or have been successful. Once we're kind of moved past that phase, which we might call the response phase, we're in the kind of proof of freedom or area of freedom phase, which is providing evidence again that the pest is no longer there, and that facilitates trade and market access. And then finally, this is probably more specific to industry, is monitoring, and that's associated with that containment and eradication phase, but also once we potentially have a pest, growers, doing trapping and surveillance to know what the kind of management looks like. So in a nutshell, it's basically, is it here? Where is it? Is it under control? Is it gone? And if it's not, what's the population status? And so when we're designing a program, we need to consider a lot of different things. I just spoke about that. What is my surveillance goal? Am I looking at early detection, delimitation? What do I want to know? And that is very important when you're designing a surveillance program. Knowing thine enemies. So, what does it look like? How do I diagnose it? And that's where Paul will come in with his NDPs and talk about those later. There's not a lot of point looking for a pest if you can't actually identify it in the first place. And Paul will give you a lecture on how molecular is far superior to morphological, and shit over every entomologist in the meeting. Then we get into kind of where should I look? This is where James comes in. Which pathway? How's it going to come in? How far could it spread? What are the preferred hosts? These are all very important questions when we're designing any type of surveillance program. When should I look? Is it seasonal? Does it die pause? There's certain times of the day when it's active. Again, all very important. How do I find it? This is probably what a technical reference guide talks about most and covers most, which is, what surveillance method is best? Should I be trapping? Which traps work best? There's lots available in some instances, and they're all not necessarily the best. Should I be using a lure? Is there lure? Is visual surveillance the better option? What do I need to do? And having a place where I can look up this information and get, highly endorsed recommendations is very important. And finally, and we don't get into it much here, is the question about how you capture the data. Is there an agreed app? Is there a data standard? And those appear within the technical reference guide. And where should it go? Is it just going to sit on my system? Are we going to try and put it in a national collation system like AUSVEG? Should it end up somewhere in Biosecurity Commons so that we can do risk analysis? Those are all the questions that I need to consider. And that's just reiterated everything I just said. The surveillance goal will impact on the design of your program and the relevance of each of those questions. And how do I know what's important, what's not? What should I do? I would consult the Subcommittee for National Plant Health Surveillance, or SNF's, technical reference guide. So this is just a brief history, which I won't even bother going through. But basically, back in the day, everyone recognised that consistency in surveillance approaches and methodology was very important, so that we could make very strong claims for area freedom and or have an early detection program that was most likely to succeed. And so this is what we have today, 10 years later. Again, we've changed the scope a little bit to be more comprehensive in terms of those surveillance goals. They did start generally focused on early detection, but they've been expanded to include all of those surveillance goals now. That's the table of contents. And I'll highlight a couple of things. The 3.2, where and when to conduct surveillance. So the entry and establishment pathways these days is a bit of a placeholder for the type of work that James does. And so all of these kind of streams really kind of link together and fit into the NSP structure. In a perfect world, one day we'll make these modular, but at the moment they'll be kind of online documents. So just reading through that stuff on the right is the technical reference guide is the first point of reference for developing surveillance plans across a broad range of surveillance goals, provides direction and recommended approaches for conducting surveillance on a specific plant pest or group of plant pests. Again, we're trying to find a way to group certain pests, leaf miners, for instance, together when there's similarities between how you would capture them and their biology. They provide a mechanism to ensure that contemporary science and surveillance practices are applied and all relevant information is included in a consistent manner across all surveillance programs. This is very important from the kind of Commonwealth market access side of things. We need to know that the surveillance that we're doing is kind of gold standard, so that we're making claims of freedom and talking about market access. Trading partners trust the data that we're putting forward. And they contribute significantly to that, achieving that goal of a coordinated surveillance system. We do like to point out it's not a one-stop shop, and so you will rely on additional resources such as the NDPs, the preparedness plans, your own organisation or industry's SOPs, and then decision support tools such as Biosecurity Commons. So they're designed to all kind of work holistically, and I think we're kind of slowly getting there. So just as a real world example, I know everyone loves acronyms, so I'm going to throw a whole bunch at you. WTF, NPPP, TPP, VIC, POF, CCEPP, TRG. So, oh no, the national priority plant pest tomato potato psyllid has been detected in Victoria. How do I design a surveillance program to demonstrate proof of freedom to the Consultative Committee for Emergency Plant Pests? I know, I'll consult the Tomato Potato Psyllid Technical Reference Guide. So this is a real world scenario. This happened around this time last year. It's no big secret that TPP turned up on the Ballaring, and as is known to occur, I was asked to write a surveillance plan pretty quickly. And so again, I had to consider all of those aspects I talked about earlier. What is my surveillance goal? Well, it was delimitation, containment, and proof of freedom. We needed to be able to demonstrate that TPP was confined to the property and hadn't spread. Knowing that enemy, there's an NDP, great. So we know how to diagnose it, both through morphology and through molecular analysis, and our diagnosticians had the capacity to do that. Where should I look? We've got a host list, isn't that great? And I worked with James to predict the spread about how far it could potentially go so that we could start talking about restricted areas and proof of freedom. And James will probably touch on that in his presentation. When should I look? This happened quite close in kind of spring, and we were going to carry on surveillance over the kind of summer period, but looking at the draft technical reference guide, it was very clear that the hot summers were not the best time of year to do surveillance for TPP, and that could potentially bias our results and make us think that it's not there because the conditions weren't right to find it. We looked at how to find it. We went with sweep netting and green sticky traps again. Traditionally, we use yellow sticky traps, but when we dove really deep and did all of the kind of research when developing the technical reference guide, there's evidence and publications that show that the green sticky traps are far superior. So again, we're getting that kind of evidence-based guidance on what we should be doing in our surveillance program. In terms of how we capture it, AUSVEG has its own program called TrapBase, which is used nationally, and there's data protocols established for that. So based on all of that, Agriculture Victoria were able to set up an appropriate restricted area and design an effective surveillance program based on the tools we had at our disposal. Our training partners and industry were comfortable with maintaining area of freedom outside of the RA, and the trade and market access was not impacted. And this approach demonstrates the importance of using evidence-based decision-making and the need to have multiple tools that complement one another in our biosecurity toolkit. I think most of you know that's not the end of the story. And so we have another bunch of acronyms: TPP, NTFE, NPPP, CLSO, VIC, POA, CCPP, TRG. Oh no, tomato potato psyllid is not technically feasible to eradicate because we've found it elsewhere. The National Priority Plant Pest, I can't even pronounce that, could present CLSO, could be present, which is separate chip. How to design a program to demonstrate proof of absence. So once again, here I am, I've been asked to design a surveillance program for CLSO, and I'm looking to the technical reference guide on information on how to design an appropriate program. So that is it for me. I rushed through it. So apologies if it was a bit rushed.
That was great. Thank you, Tim. I really liked the case study in that. If there are no questions in the chat, I'm just going to take a step back to Paul because I made a mistake and I accidentally skipped Paul before Tim. So we're just going to go back to the diagnostic protocols before we continue on the surveillance journey, and James will share how the work that he does supported what Tim's surveillance design. So I will now hand over to Paul Campbell. So Paul is the Principal Plant Pathologist at Queensland. I think you're still the Department of Primary Industries. And so Paul leads the diagnostic component or diagnostic theme of the VegWatch program. So when we find a pest, very important to make sure that we know it is what we think it is.
Thanks, Rose. Yeah, so Tim just went through how you look for it, and our thing is, we're going to make sure it's correct. So wait a minute, let's try that. So basically, it just comes down to, we just want to know exactly what it is. That's the big question, and can be quite a big answer sometimes. People like to put things into boxes. We started officially naming things back in the mid-1700s. Virologists got on board about 270 years later with the whole binomial name thing. The boxes we use through science expand and contract. So, that species might become 10 species later on. It might contract back down to only a few species. So actually knowing what it is a big important thing, especially when you start looking at government stuff. So once you start putting things on national priority lists and things like that, more resources become available for surveillance or for detection and things like that. So in personal cases, you wake up one morning with a little headache and you take a COVID test, you get a week's free holiday, basically, mandated holiday. If you didn't have that diagnostic available, you'd probably still have to go to work and maybe kill somebody. So knowing what you're doing and what you're finding is really big. The whole idea of having available national diagnostic protocols is to move from that I have no idea what it is to, yes, Your Honour, I know exactly what that is, and I can guarantee that that's why we shut the industry down. Or not. So a lot of the times these things happen in real time. So something occurs, we don't know what it is, we're tracking down, we're trying to develop diagnostics and work out why they're working or not working as we're going through, and it just doesn't work very well at all. In this project, we're focusing mainly on national diagnostic protocols because we want consistency in diagnostics. Anyone from Darwin, Brisbane, Melbourne should get the same answer for the same pest every time, accurately. So obviously there's no point doing a diagnostic if it's not accurate. And then basically the confidence. We don't trust anybody, least of all myself or other people. So if you have, I've followed the National Diagnostic Protocol and it's worked fine, then we have confidence in moving on to what we have to do through surveillance and things like that. And just the availability, if it's there and it's ready to go. So the main parts of the National Diagnostic Protocols are detection, so mainly symptomatic stuff, what to look for when you're looking for it. That helps to inform surveillance activities. Where to look on the plants, usually where to sample on the plants, how to keep the sample good so when it arrives at a lab or whatever, it's still usable. The main part of the National Diagnostic Protocol is the identifying. So how to ID, if it's a pest, how to key it out, what it's going to be different with, like what's it confused with, what are you going to have trouble with local things, or maybe some other overseas things it could be confused with. And usually not so much for pests, but they're getting more and more, just about everything else, fungi, viruses, bacteria, all molecular. And now it's basically molecular options. So if you have a qPCR machine, there's a qPCR in there. If you only have an ordinary PCR machine, there's ordinary PCRs in there. There may be near field diagnostics as well. So the ability to scale your diagnostic for the lab that's actually doing the test is very important. And then there's a bunch of other stuff. Host lists are also part of this. That seems to be part of everything. But then there's a section 9 now, which is the detection through surveillance. So near field, quick tests, high throughput tests, etc. So we try and work all of that together into the National Diagnostic Protocols. So how do we go about making one? Basically, you go back to how did they decide that that was a separate species? So that basic description, you start from there and work up. You go looking at the literature. Someone in the 1600s described it on a potato once and it's never been seen on a potato since. Is it still a pest of potato? Yes, no. It's difficult, and that's probably the hardest bit because everyone wants to publish something that they've found that's exciting. A lot of people don't publish stuff that's not exciting. They've seen it for the last 200 years in this one spot. Who cares? So you've got to wash off the novelty and get down to the actual things. And sometimes it helps talking to overseas people as well. Then if you can, go get some for yourself so you can see what it is in real life. Usually dead. It's a lot easier if it's dead. And if you can spread it around the country, not in that way, but into labs in ethanol or something like that, helps the diagnostic ability for pretty much the entire country. So if we can, for this project, we're trying to target priority species and obtain specimens for them for diagnostic labs that would most likely be dealing with them. We then go find some tests, or we design some tests, more likely design tests, and then we test the tests. And that's really the bulk of it, because we've got a lot of weird species in Australia that people have never run up against. We have to try and validate the tests against them. So then you have to validate and verify. they're pretty much interchangeable. The NDP people have decided that validation is making sure the test works right and does what you want it to do, and verification is getting someone else to be able to do it as well. So you're testing all sorts of specificity, sensitivity, repeatability. I can't even say it. I won't repeat it. Diagnostic specificity. So you cut off detection, you start going around and around in a circle as many times as you can in that space until you run out of money and time. And then it's the best test you have at the time. There's no such thing as a perfect diagnostic test, especially when you're dealing with plants, because you'll try it off in some weed and it just doesn't work. Then you move into verification, which is the main bit of the NDP. So you try and test it at least one other lab. They have different equipment, different procedures, different people. It might not be on a mystical line that makes everything work well, like our lab. You set up reference panels to get a bunch of people to test it. And at the end of the day, it gets accredited. So it should be able to be pulled off the shelf and grabbed and run for a diagnostic. So someone turns up and goes, I think we've found TPP. It's lucky we've got, go into the library, we do have a diagnostic protocol for TPP. Looking at the bottom, it's not too bad, but it's not great. It's from 2012, supposed to be updated in 2017. That's a few years past that now. But morphologically, it works fine. Luckily, there's not too much that can be confused with TPP. So you go off and you look down the microscope, look at its wings, blah, blah, blah. And yes, it's TPP. And then you high five the surveillance guys and off they go to do surveillance. Works really well. Next problem is the surveillance guys come back and they have more than you ever wanted because you didn't set limits on how many you can possibly test through looking at your microscope at one time, which is where that section 9 comes in importance. The TPP one doesn't currently have one. There is a test as part of the CLSO one, which makes it really good. So there is molecular tests for that because sometimes they're like, here's a trap at 300 flies or something. Can you tell me whether there's a TPP in it in an hour or two? And even pulling flies off sticky traps is a terrible business. So you need to have a range, if possible, of things that will work on the design things from the surveillance trap. And then, as Tim was saying, is there CLSO? So yes, there's a diagnostic protocol. When it first came into WA, the diagnostic protocol was not the best. It gave quite a few false positives. So there was projects that worked on that, and now we are currently in part of this project finishing up the rewriting of that. They've been tested. We gave a workshop, and I think we gave it to like 7 or 8 labs across the country that wanted to have it. So we gave positive controls and tests, and they've all run it, and they all say it's fine. So it's probably as verified as the protocol is going to get, and you can take it off and wait for the surveillance guys to turn up with the boxes full of plants to test for everything that we've got. And that's me.
Paul, from your experience, how frequently do molecular diagnostic methods change for priority plant pests and diseases? Or is it too variable between species to say?
If you're talking, let's just roll through them. Viruses, they change because the taxonomy changes, basically. There's not much, some things suddenly fall out as a different subgroup, it turns into a new species, so the diagnostic will have to change. Bacteria and fungi are pretty much the same because the taxonomy changes. It's the more sequencing we do of those, the more it's going to change. And the molecular diagnostics usually have to change if you try it on a nightshade and suddenly it gives you false positives. So you have to change regions. That's the other main region. And so the more of this verification you do at the beginning, the more chance you have of identifying that so they don't have to change for 10 years or so. In pests, again, the taxonomy might not change, though sometimes it does. It's just getting more infects and things actually sequenced might find that it does give you false positives for something else. Again, more verification, validation you can do, the better.
I will now hand over to James Kamak, who is the Chief Investigator at the Centre of Excellence for Biosecurity Risk Analysis and the Program Manager of Biosecurity Commons. So he's going to explain some of the background, I guess, to what Tim presented in the surveillance in terms of how we decide where to do surveillance and lots of other stuff.
First off, it's great to be here today. What I'll be talking about is basically how do we operationalise the work that, say, Tim and Paul and Stephen's done in terms of thinking about what's those priority threats that we really care about, right? How are we going to do surveillance and how are we going to do that diagnostics? Basically, Tim's provided the broad overview of what a technical reference guide is, and Paul's done the equivalent for diagnostics. The question that remains is how do we actually operationalise that? So we've got these technical reference guides that can tell us, we need to use this type of trap and put it in these types of locations. But the problem that practitioners, particularly surveillance practitioners, face is surveillance and diagnostics is extremely expensive. We can't just put it willy-nilly everywhere. There needs to be some risk-based information about where we focus our resources. So what I'll be talking about is basically how do we combine that biology and mathematical models to estimate risk and forecast risk to help us inform questions about where to focus our surveillance and how much surveillance we should be doing. So when I started working on the VegWatch project, the initial focus was thinking about exotic threats coming into the country, and largely that's thinking about how do we estimate establishment potential risk maps. And I'm not going to go into huge detail about this particular method because I'm going to focus on the TPP risk mapping and spread modelling component. But I have done some work in this space where we're modelling, say, BMSB establishment potential, but also TPP in the eastern states before we had the incursion, and we're doing this for other threats. But the main thing to realise is that we only really care about locations where the threat can potentially establish, right? There is always going to be transient populations that will show up in a given location. Let's say it's in the middle of the desert. It's unlikely to have a suitable habitat or the climate's not suitable for it to establish, and it'll just die out. So the main thing you need to think about when you're thinking about where to put surveillance, particularly for early detection for those exotic threats or those endemic threats that are not in certain parts of the Australian landscape, is establishment potential. And that broadly comes down to thinking about three fundamental factors. Can it get there? So what's the pathways of entry? And there's many different ways for an exotic threat that can come into the country. It could be related to international trade, such as movements of containers, vessels, international mail, imported goods. It could be related to human movement, international passengers, returning passengers, or smuggling of animals or plant parts. And of course, then there's the natural pathways of entry. So we're thinking about the Asian citrus psyllid up in the north, potentially being blown onto mainland Australia. Or, in terms of TPP, natural movements from WA across to the east coast. A pest can only establish if all three factors are viable. So it can arrive at a location, the climate or the abiotic suitability is suitable, and the biotic environment is suitable. And as Steph raised in her first question, this is all going to change under climate change. Pathways will change, so trade routes will change, and the volumes of trade coming from different locations around the world. The climate suitability of a threat will change, and of course the habitat's going to change with that as well. So basically, we can use all this information to build models that approximate establishment potential. And this is really, really critical for both preparedness and early detection surveillance plans, but also can feed back into the work that Stephen's been doing in terms of what's that prioritisation of those threats. What I'm really going to talk about today is the case study of tomato potato psyllid incursion in the Bellarine Peninsula. As Tim pointed out, we know it's established in the Bellarine Peninsula, and Tim needs to now tackle a series of questions. Where has it potentially spread to? Where should we focus our surveillance, and how much surveillance should we do, and for how long? Right. And so this little blue dot is the initial incursion that was detected. And what I was tasked to do was to try and build a spread model that could forecast where it's potentially spread based on information that we know about that particular location. And to do that involves many, many different types of models. So in the model that I developed for this particular case study is I used a population spread model. So I needed to first understand how quickly the species can, its population growth rate will grow. And so to do that, I need to know information about development times and survival from eggs to larvae to pupae to adults, or in nymphs in this case. This is just an example. Right, so I can build a population matrix model that can simulate how the population will grow, and we can make it dynamic, spatially dynamic and temporally dynamic by accounting for seasonal changes in temperature, for example. But that's just the population. We also need to know how the pest may move or spread across the landscape, and that's going to be a combination of natural movements, so natural dispersal movements, so it's often a diffusion style model, but also human-mediated movements. So we need to know some indication of how far, on average, people around metropolitan Melbourne will likely move on a given day. And so we can pull some of that data from commuting statistics from the ABS. We can pull population dynamic data from the literature, where there's entomologists love doing life table analysis and seeing how species respond to temperatures. But we also need to combine it with landscape suitability. So where in the across the landscape is it likely to be climatically suitable? So that's a species distribution model. But also where's the suitable habitat or host material? And that could be a combination of land use, vegetation type, information about the distribution of weeds, and all that sort of stuff. And so what we've done is we've developed basically a model that encapsulates as much of that biological information as possible. And what we've got is this little red dot that was here originally was the initial incursion. And what you'll see as this progresses, this is done on a weekly basis, but it's updated every month, so every 4 weeks, is you can see how this population will gradually spread. Starts off quite in purple, so low probability spread events, but as time progresses, that spread and the probability of it being present in that location increases. And so this particular model encapsulates information about natural dispersal movements that we've derived information from the literature, human movements, so knowing something about the distance that on average a person may travel per week. And we've also got seasonal dynamics. So for example, how does the average temperature likely impact the intrinsic growth rate of the population? The really good thing about this model is it's got a lot of detailed information embedded in it, but it's very easily extendable. So it can be updated as we get new information. So that could be new information about human movements, for example, or new information about how populations may vary as a function of temperature or precipitation. Or we may have new spatial layers that may that are being developed by other people that might further refine this model. And so as you can see here, we're starting to get some warmer colours here. And so this particular location here, I don't know if you can see my mouse, but it's getting close to 60 to 80% now chance that the pest is present. And there's some indication that that's actually what's actually happened. The other really useful thing about this model, and this will feed into Guy's presentation later on, is that we can also collate additional information that might be obtained through traceability apps such as what OnSite offers. We can take outputs from a spread model. So if we think that the threat has potentially been present at the location for, say, 2 years, we can then basically take the projected simulated spread model for that location, and then we can feed it into an optimal surveillance design, where we can specify the type of trap, and as a consequence, the efficacy, so the probability that a trap will detect a pest that's present. And we can account for surveillance and diagnostic costs, and we can make a budget constraint, because invariably all regulators have a budget constraint in terms of what they can actually implement on the ground. And as Tim pointed out, there's multiple surveillance objectives. So if it's for early detection, we want to maximise the probability of detecting at least one incursion, or one incursion site. Or it could be in relation to delimitation, where we want to maximise the number of detections. Or in the case of area freedom or proof of freedom, we want to know how long do we need to sample a location and get nil detections before we can be confident that the pest has been eradicated or the area is free of a threat. This particular model here is just a hypothetical, where basically I can feed in all this information that comes from Tim's work and with a budget constraint, and it'll basically tell me where we should be prioritising our surveillance. So in this red areas, this is where we're most confident that threat is present. It's saying per 1 kilometre grid cell, we want to put about 5 traps. Whereas out towards Geelong over here, we need about 3, because the risk is slightly lower there. So these models here are being directly used. They're a product of the VegWatch project, and they're being directly used by Tim and his surveillance team for informing where to focus their surveillance for delimitation and also potentially monitoring. So the one thing I want to point out with this is that these models have traditionally been done by risk analysts. They're done once off sort of thing, and then they disappear into the ether. And that's problematic, because what ends up happening is we continually reinvent the wheel, and that leads to significant delays in robust science-based decisions, which have major consequences for industry, right? Because if there's delays in decisions, businesses are locked out of market for longer. And so what we're doing in this project is we're developing these template models. So for example, a TPP spread model and surveillance design that, while it's in this case being applied to the incursion in the Bellarine Peninsula, it's very easy to take this model and apply elsewhere. And the way we've done this is we've developed these models on the cloud computing platform called Biosecurity Commons. So it's a publicly available, free for everyone to use analytics platform, where we're continually building up a series of case studies, and the TPP one, and we've got a BMSB one as well. We'll have these templates that, for example, if there's an incursion in Queensland of TPP, they can take this model. They don't have to wait for another model to be built, and they can apply it based on the information they've got under their context. The really good thing about this is it's cloud-based, so you don't have to have a supercomputer to run these models. We use the Nectar Cloud infrastructure. The models are reproducible, right, and can easily be updatable, and it's secure and shareable. So, for example, the model that I've developed, I've shared with Dika, so Tim can use. Similar models can be developed by others and can be shared across jurisdictions or across industry. And all this will ultimately lead to better risk management and faster decision making. The last little bit that I want to point out here is that while I've only just focused on surveillance and spread modelling, the the spread models can be really, really useful for other contexts. All right. And so Aaron Dodd, who I know is in the meeting somewhere, has been instrumental in doing some of this early work for SEBRA back in the day. But if we have a spread model and we know where the assets are, so the assets that we're trying to protect, so in this case, the vegetable industry, and we know something about the value of that industry, and we link it to some of the work that Stephen's done, where he's thinking about what's the impact to industry. What we can do is we can simulate spread, right? And also quantify what those potential impacts are to those assets. So that's really useful for industry to have an understanding. If a threat gets into a location, right, and we know something about its spread rates and all that sort of stuff, it brings all that information together and produces outputs that are directly useful for industry for thinking about what's the potential damage to our sector, and therefore how much money should we be willing to spend to adapt or to control or to contain an outbreak. These models can also be applied. So we're thinking in the top diagram where we're looking at unmitigated scenarios. So we let it rip. Whereas the bottom one is we impose a surveillance and control plan. So as you can see in the second one, we've got a surveillance plan where we're detecting things really quickly, right? And then we're imposing a control treatment on that. And as you can see on the right diagrams here, the changes in the monetary loss or the impacts declines as we contain and control that spread. That's really, really useful because that can be used by both industry and government for thinking about how do we best prioritise R&D investment. Do we want to focus on improving the diagnostics of a test or the effectiveness of a surveillance trap, or the control measure of that could be imposed if we detect something? So all of this can ultimately lead to better preparedness and faster decisions and responses, and this ultimately leads to faster industry recovery and greater industry confidence in the system. And I'll leave it there.
Thanks, James. I'll just point out one of the challenges that the vegetable industry has is that we don't necessarily have a clear understanding of which crop is grown where, because vegetables are short season or short-term crops. Unlike a tree crop, it can be a bit challenging to do the mapping and know which crop is in the ground at which particular time of the year. So I think, it's great if you've got a tree crop that's in the ground for many years. It makes it a little bit simpler to map your production areas, I think. So there's a question from Brendan in the chat. So could your analysis influence the setting of the budget constraint by showing the marginal benefit of increasing the budget?
I love that question. Yes. So it can, and in fact, that's a pipeline development that we've got currently set to go on to Biosecurity Commons next year. It's going to be a resource allocation model. So SEBRA as a group have also been working with the New Zealand government on this model that Tom Compass leads called Value Max, which is to do exactly what you're suggesting. The really good thing about it is it can be done across the entire biosecurity system, so it's from pre-border, border, and post-border, or it can be done across threats. All right, so it'll help optimize for a given budget where you should be allocating your resources. The other way you could do it using the current system is you could basically run the model multiple times with different budgets. All right, that's the slower way of doing it, but there's some work in the pipeline to really try and make it easier to calculate those marginal benefits.
Are there any other questions for James? Okay, so one of the things I've just mentioned was that within the vegetable industry, it can be quite challenging to know which crop is grown where on a particular farm at any given time because of the shorter season or the annual cropping, the nature of the vegetable crop itself. And also James's modelling is at a different level, of the movements that are happening within the farm. So this program also partnered with Onside, who have an on-farm check-in app, and it can monitor who comes on and off farm. So I'm going to hand over to Guy Davidson now, who's the head of customer with Onsite, and he will present the outcomes of what the Onsite component of this program has found.
Yeah, thanks for the intro, Rose. So I'm Guy, I'm the head of customer at Onsite, been with the company about 7 years. You know, this is the latest in a series of different sort of industry government tracing projects that were done. So this vegetable sector one was the latest. We did one with the New South Wales DPI and New South Wales wine industry a couple of years back, and then we've also worked across probably 8 different sectors now in New Zealand as well, because we're based from New Zealand, moved to Australia 5 years ago. So yeah, we've worked across many different sectors using this sort of technology and insights in a similar way. The kiwi fruit sector and wine sector in New Zealand have it as an always-on solution now, so that's kind of the end goal of any of these projects. And so just a bit of background on Onsite, I know a lot of you might be new to, we're our own best kept secret, so just so you guys actually know the business and what it's about. We started about 10 years ago in New Zealand, came from the dairy sector. It was very much about knowing who's on property in real time and actually was around health and safety compliance, but we've evolved into a consolidated platform that spans across biosecurity, safety, contractor management, operational tasks, farm mapping, a whole bunch of different areas. We've currently got 21,500 farms that are mapped within the solution across New Zealand, Australia, a little bit in the UK, and starting to push into the US as well. And so for this project in particular, we were involved for 18 months from the beginning of the program. We got 73 farms opted into sharing data, tracing data for this pilot project that we did. There was a mixture of Victorian, Tasmanian and Queensland farms. Majority were in Vic, second largest Tas, and then a smaller portfolio in Queensland. We collected over 1,000 movements across all of these farms through those probably, I think, 12 months, maybe less than 12 months, we're actively collecting the data. The sort of initial stage was setting it all up. And, you know, the sort of summary of everything, which we'll go through how we get there, but the summary is really that within these 73 farms, we are able to identify 10 key farms that, if monitored correctly, reduce the rate of spread by 90.5%. So they have a disproportionate impact on spreading something throughout the network of the farms that we had on the pilot program, and that's pretty common no matter how much you scale up a network like this. So in terms of the operational nuts and bolts of how it all works, basically we have a product that can geofence a property, so a farm. We also have either app-based, QR code, or kiosk-based sign-ins. All of them are attached to the single property, so the tracing data collected through any of those methods will be attached to a single geofence, a single property, and essentially, visitors, contractors, staff, etc. We try and get anyone that interacts with that farm to sign in and out. That's collecting your robust tracing records, and then as people start to move from property to property, you start to build a network of connections of movements. So, you know, very much complementary to what James was just going through before. That's very natural spread modeling and using those sort of data, whereas this can overlay and help, I guess, show the unnatural spread of how people, machinery, equipment, plants, etc. can move these pests and diseases in a way that wouldn't naturally occur. And so going through an example with actual data that we collected throughout the pilot project, and I've put a big bold statement at the bottom of all of these that this is an example scenario, because I've heard horror stories of people taking these out of context to be a real scenario. So as an example, say there is TPP found on this property here in Bacchus Marsh. What we can do is, with the Onsite technology, we can automatically plug in that this is an infected premise. We can set parameters that we want to say how long do we want to know any directly connected movements, both trace forward and trace back from that property, because it may not be ground zero. We might want to know where it could have come from, and it certainly could have spread further outside of the initial radius that's around the property. So as we put those initial parameters in, you might get some results like this, and this might be kind of expected. There's some nearby properties that it connects to, both with trace forward and trace back movements. But what we find time and time again, and we found in this project as well, is that there's actually these other movements. And Tim was talking about the delimiting surveying before. We can actually automatically and in real time show where some of these outlier nodes or properties might be that we know have connecting movements to that infected premise. And so you can straight away see with this example that I put in, and this is using real data, if this property in Bacchus Marsh were to have a disease, say TPP, and we suspect it might have been moved by humans, vehicles, plant material, etc., the data on site had collected even through this pilot project shows that it could be all the way over the other side of Melbourne by now. And so you'd want to go and start at those properties to make sure that it hadn't got that far and you're not dealing with another network. And so if you did find that it was actually out on one of those properties, this is what it might look like. So you see down on the right-hand corner of the picture, I've just included some of these other properties here saying, hey, these are actually now non-infected properties. You add them to the tracing movement and you can see it actually starts to spread out to a few different areas, and there's much more volume of connections back and forth between these properties as you start to add a few more into the tracing. So you can keep expanding on that as far as you need to every time you find a new infected premise. You can step things out. So this is looking at directly connected movements. You can also go, what are any properties connected 2 steps away? So it could be someone's gone from property A to B, then C, and you can step that out as many times as you need to start to see how the chain of events might have happened and where the connections might lie. What you can do from there, so that's really just using the actual data to show connections, and that's useful, but at scale, that becomes very hard to manage. So, it's great to have the data in the first place, but once you scale that up, it's very hard to prioritize and understand, which are the properties that you should go and prioritize for response or put active surveillance on for the best bang for early detection. And so what we can also do is we can layer in network science algorithms. And so we have a colleague that is actually, his day job is working at Google in New York, but he is a network scientist by trade. He studied with our CEO. They both did their PhDs over in Cornell University out of Ithaca, just out of New York. And so his background is really being able to take large complex networks and break them down to show the priority nodes or properties in this case in the network that if you put early detection on or surveillance on, or if you responded first and essentially cut them out of the network, they're going to have the biggest impact on early detection, or in the case of a response, stopping the spread and trying to contain from people movements. Obviously, James's models will show the natural spread and stuff as well. So to put this in a simple way, this diagram up the top here kind of explains it. And, it's no different to the COVID stuff. Everyone's talking about clusters and separating clusters, etc. So you may have all these properties within the veggie sector, for example, but there'll be these super blocker properties that basically connect the bridge between 2 complex and, very consolidated networks that will spread like wildfire if it gets in there. So by knowing which ones these are, having constant surveillance or removing or restricting movements on these specific properties in a response, you can eliminate or at least reduce the risk of it going from one side of the network to the other and significantly reduce the impact that it has across the wider sector. And this doesn't have to be just sector by sector. We work across all rural sectors, so certain pests and diseases don't care about, Victoria as a state, or don't care about just the vegetable sector. They're going to go where they thrive based on, James's models are the same. They'll just look at habitat, they'll look at natural spread, all that. And so we can scale that up as well to go, if it's brown marmorated stink bug, what are all the sectors that this might impact and it might go across? Because it may be, an orchard that actually is the best property to have surveillance on through a whole network to actually protect the vegetable sector at the end of the day. So being able to look at those insights across a whole of the industry and multi-industries is extremely useful and quite complex to get. The way we're able to get the data, because that's the toughest part, is actually getting people to actively engage with something that collects movement data of people, machinery, plant material, day in and day out. Because if it's just for one purpose, biosecurity, and they don't see a return value day to day, it is very hard to get that consistent engagement. Like you see with the COVID app, right? Like no one uses that anymore because it's not such a big threat. At the time when it was on the doorstep and everyone was really worried, they used it a lot. Our tool is primarily and originally based as an operational tool, and so that's why people engage with it day to day. And we actually saw, Rose and I were looking at the data because our proactive engagement ended maybe 6 months ago, maybe a bit less than that. So we haven't been actively driving the use, but we've left it on for the pilot participants. And I looked at it the other day and the usage hasn't dropped at all. So once someone adopts something like this for their own operational use day to day on their farms, they'll continue to use it. And so because they're using it for what's useful to them day to day, they'll be collecting the movement data that's useful in a response, or, you know, to use for surveillance prioritization as well. So that's a real quick overview of how this all works. There's a lot of detail underneath it all, and I'm happy to take anyone that's interested through that at a later date.
Just to summarise where we're at, we're building our emergency response capability within AUSVEG and the greater biosecurity, the greater vegetable industry. So we've had quite a lot of training conducted by Plant Health Australia for our board, our team here in the AUSVEG office, and next year we're looking at scenario exercises with growers and agronomists in different regions. We now have almost an endorsed biosecurity plan and our priority pest list. So just looking, and we've identified which of those pests and diseases we have prioritised for the development of diagnostic protocols, risk maps, and surveillance protocols. And next step is to develop what we're calling spots or single points of truth or continuity plans for those priority pests. So I mentioned earlier about whether we go to eradication or to management, like what do we need to have in place for that to happen. And then the big next step is to develop a system and framework to collect and store and analyse and apply data collected during pest monitoring activities led by industry or conducted by industry. So that's proved a little more challenging than what we first anticipated. We're looking at an industry-led surveillance, more controlled, I guess, monitoring program, which will start very shortly. And then we have also been working in the farm biosecurity space. So we have a new farm biosecurity manual to promote, and it's interactive, that you can type into to promote the development of biosecurity plans by farming businesses. So that's the link to the plan there. If you want any more information about the program, you can get in touch with me or anyone else that's presented today. I'd like to say a very, very big thank you to the VegWatch team. They're awesome people to work with, as you can see by what they've presented today. This program wouldn't exist without them and their energy and the ideas and energy that they bring to the program. So I'm very grateful to be working with such a bunch of great people. Thanks also to Carol, who's the video producer in the background today, making sure this all runs quite smoothly. Thank you all for coming, and I hope you found some useful information that you can apply to your own industries or organisations. So thank you and take care, and we'll see you next time.